starting the live stream. This is D. Thomas, Map Guru. They call me the Data Beast. We're starting to get class is starting to get a little bit more intense. Statistics is starting to get more advanced. We're starting to conduct full experiments. We're starting to learn how to reproduce the data and set up our data to be reproduced, which bothers me a little bit because I've always had this fear that people will just steal my idea, take my work, and run with it. But then when I started to think more and more about it, I realized that there's just so many projects out there that it's okay if someone takes my idea. I can just have another idea. And again, it works both ways. So, yeah, open data, it is. Or it is. We're going live. Hit me up. Follow the stream, man. This is Database. They asked me, say, hey, what is your motivation for studying data science at SMU? What kind of question is that? What is my motivation? I told them I just want to make money and buy a house. That's what I told them. And I want to do it gracefully, with style and grace. So I want to graduate the first top of the class out of 70 people. I want to be number one. That's what I told them. Let me in. I'm saying I'm happy to even be in here. A lot of people don't even know that about me. I'm a beast. I'm only getting smarter and smarter. I teach people this. I teach statistics. And I ain't even had no statistics class. I teach linear algebra. Got my math degree back in the 90s, man. Very authentic. We didn't have calculators and things to use the internet. We built the internet, man. Come on. My roommate became he built Twitter. He worked at Google, Twitter, Yahoo. He mastered JavaScript, and this was my roommate, a kid that didn't know a lick about computer science. He just picked up his book and started it and went crazy. His major was Spanish. And shout out to my boy Dustin Diaz, man. They don't want the real math heads to control the computers, because we're gonna take it to another level. I'm a beast on it, man. We just told them, man, I'm looking past masters. I want a PhD. I want to teach some classes online. Can I teach some classes online? Please? Oh, man. For real. let's say, suppose we got two data sets, fired and hired. You either fired or hired, right? And we have 12. Actually, let's turn that into a 22. Be fired at the age of 12 is a little inaccurate. So let's just say, we want to see if there's a difference between some sort of systemic hiring and firing mechanism based on the ages of the two groups. Because everybody knows that you're not supposed to discriminate against age, anything categorical. Sexism, whether your sex, whether your age, your height, your weight, your ethnicity, all of those social justice issues that come up, So what we would do is calculate the mean. Let's see over here. It's not pen is sensitive. All of those statistics, deviation, everything. Same thing here. We did the mean of H, the mean of F, and we subtract those. So what we'll do is we'll make our null hypothesis. Is it true that the real population of F equals this, and then consequently our alternative, which is what we're trying to show. This is like a proof, but it's not a proof. It's a hypothesis test. Say that these are not equal. And again, I actually prefer this notation because it helps with my language. That the difference, it helps with my understanding, is the difference between the fired and hired is 0. It means that there is no difference. And consequently, that the difference, the alternative is that the difference between the fired and hired is not 0. So meaning, it's not 0. Now the problem is if we do a t-test, there are assumptions. Now, because our data is small, it's already violated one of the assumptions of the t-test. And even if we did try to graph this, it'd be really difficult to try to see if the data was pulled from a normal set or not. And so, because of the t-test is not that reliable, what we would do is just calculate the difference of means. Because we want to infer about the difference of means. Now, what we're going to use is a permutation test. A permutation test can be used to infer any different statistic, whether we're talking about the mean, the deviation, all of these different things. But what we're going to focus in on is the difference of means. Permutation test can't give you no confidence interval. Those shouldn't even be on the same sentence. If we're talking about a test of the difference of means, that's something entirely different than a confidence interval. And even if we were to observe the confidence interval and then use a permutation test, we're going to be having thousands of confidence intervals. How will we select the confidence interval? We choose all the confidence intervals that have the same range to be our confidence interval. We don't have the code to do that. That's a very complicated piece of code. Instead, what we could do is transform the data, and based on the ratio of the means, we can infer the ratio of the medians, rather, we can infer about the actual size of the population based on that ratio. And that actually was a problem from the homework 2. And I if you don't believe me, I will pull up my homework 2 and show you. We're not playing in here. It's time, and then the course gets tough. It's time for you to get tough. You got to get tougher than the course. When stuff get hard, you got to get harder than the course. So you got to fight fire with fire. You got to grab the bull by its horn. You know what I'm saying? You got to grab the bull by its horn, man. I really mean that. I'm not kidding. I'm not kidding in here. It's serious business. Serious business. Serious. And we stop using the log transform. We do the ln. We need ln, natural log. If it was a natural log, I swear it would have been more straight. This is a base 10. Base 10, nobody uses base 10. So here's the ratio. The t-pool value, the probability value is less than 0.0001. Your p-value is 0.001. But that the ratio of the means, the ratio from 16 to 12 is given by the geometric mean 1.678, which implies that 16 years have 1.678 times more likely to have a higher salary, which is 67.8% higher. Now I can create a confidence interval that was given here from a 95% confidence level. There's a good chance that the true factor, the true ratio is between 1.59 and 1.95. So about 60% to 95% more. 95 times out of 100. We're not playing in here, man. I'm not here. I'm not here to play around with nobody. But look, man. Now, what I'm trying to say is a permutation test cannot give you the kind that we've studied. a permutation on the difference of means, it cannot give you no confidence interval. So let's say I calculate the mean, right? I calculated the mean, I added up, it's like 58, 114, 195, 200 and, let's just say 244 divided by 5. So 200, let's just say 245 divided by 5. That's I'll just say it's 59. And then we add these guys up. That's 2, 4, 6, 8. Plus, that's 80 plus another 13. It's 93. Plus another 63. So the difference of the means, I would say, was like so in our permutation test, this is our observed statistic. So now what we're going to do is take our data, let's see, 22, 36, 49, 56, 71, and over here we take the same amount of data, 22, 23, 23. 26, 31, 32. We take the same amount of data, we put them all together. And we create two separate groups. My first group will have 5, my second group will have 6. From anyone, all of the numbers put together, everything put together. So in other words, there's 5 plus 6, 11 observations. Well, what we'll do, we do 5 combinations in here. 1, 2, 3, 4, 5. And 6 combinations in here. 1, 2, 3, 4, 5, 6. So I can put in any number that happens to be chosen, like 71, 32, 31, 22, and then I'll choose another 23. So now by default, I gotta fill in the rest with the rest of the data. There was 222, so I can there's room for another 22. There was 223, so I can put another 23. So these are permutations. 26 we didn't use. 26 will have to be in here. 56 was not used. 49 was not used. And then also another 36. And what I do is calculate the mean of group A, and I calculate the mean of group B, and I calculate their difference. Is it greater than, equal to, or less than 33, which is the observed mean? Well, this is one permutation. I gotta do this 1,000 times. I gotta create 1,000 different permutations. We already know that there's 11 different numbers. So in essence, for first group, it's 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5, 6. There's 11 different numbers that can go in here. In actuality, even though this is categorical data, and so even though it's the age, it is not continuous. So these are like the IDs. 11 different values can go in here. 10 different values. So after 1 is in here, only 10 more. So again, if I were to do a combination, you have 11, then 10. So already between the first two different slots, there's 110 different possibilities. The first digit could be 71, 32. The first one could be any 11. The second digit could be any 10 based on any 11. So you multiply these two. You multiply this as well, down to 9, 8, 7, 6, times 5, times 4, times 3, times 2, and then there's only one left. 11 factorial different permutations possible. Well, if there's 11 different 11 factorial permutations possible, that's going to be an awful lot of two different groups that can form. And we want to see, out of all of the different combinations, how many will be greater than the observed. So let's say out of the 1,000 permutations, 352 out of the 1,000 were bigger than 33, bigger than the observed. Then that implies we can say then that the p-value is approximately then 0.352, because this is an approximation, and this is how we get our p-value from a permutation test. Now, when you're talking about getting a confidence interval from a permutation test, that's something totally different. If you do the univariate on our observed data, first of all, we shouldn't even do the univariate on the observed data because it doesn't even fit a proper t-test. But if we did, we would get a confidence interval. But we can't infer anything about it. But what you could possibly do is do a univariate on all of the different combinations based on the observed, and then you may be able to infer something about a confidence interval, but we don't have the code to do that. Now, we probably could tweak the code if we wanted to. We probably could create the code, add in, univariate on every different combination. But again, the list would be extremely large. And we would have to create a code that specifies if a confidence interval is within this realm, then we will accept it and look at the inequalities that formulate from that statement. So in other words, if you want, it's bad, it's worded not properly, if you ask me. If they're saying find a confidence interval, what they mean is, if you do not do the permutation test to find some p-value, and if you decide to do some Ttest, whether it's a single data on the differences of all the means, depending on if they're the same size and they have the same spread, then you can just create one group. And then do your Ttest on that. Yes, if it fits all your assumptions, you could do it that way, or just do the 2-sample Ttest, and then it will give you your difference in confidence intervals if necessary at that point. That's what of course, data about the mean, whether uniform or not, will be normal. Because we all know that it is assumed that the sample shares the same mean as the population. So the more samples you take and the more samples you run on every statistic, well, this is something different, but it goes back to it goes back to the discussion on uniform data. So let's just say, for the sake of argument, that the mean is 30. If we pull a sample, a random sample, every one and so what happens is that the means of the sample will gravitate towards the mean of the uniform data. And that's essential. That's one of the things about the central theorem, the central limit theorem. It's that kind of idea. So decide on a test statistic. Again, permutations can be used to calculate not just the p-value, it can be used to calculate the statistic, the test statistic, all sorts of different things. We'll call our test statistic. But remember, test statistic, this phrase is actually pretty vague. It's the statistic that we're trying to test based on our hypothesis. Well, here, one more thing. I'm gonna clear the air. I'm gonna go after this because it's getting kind of long, and I'm not really speaking about things. But you need to know what an exponential function is, guys. You need to know what an exponential function is. This is called an exponential function. I'll just put so everybody can see this. This is an exponential function. When our data is exponential, the only way to level it would take the log of it, the natural log of it. That makes it linear. So like, oh, there's so much I want to say and then get off of my chest. Like here, guys, here, let me show you. Let's say we have some kind of QQ plot. Quintel. Hello? It's exponential. That's exponential. Um, let's say we have another QQ plot. That's a square root function. Right? If I go back to decimals, we can transform the data by squaring it, and it gets it linear. Guys, we're on our way, man. We're going to wrap it up here. Just a little snippet video. We're getting good at this. We're going to get better and better. Math guru. I'm going for 100% and everything. And if they deduct stuff, they start taking points off of me, it's only going to make me go more crazy. I told them I just want to make money and buy a big house. That's it. I feel like Rambo in part 1. Then nobody's drew first blood yet. Peace, man. I love you guys, man. We're going to do this.